for the kind introduction, and hello and welcome all. Very excited to attend classes on appealing, and more than 70% of millennials and G think that our industry is dangerous. So we have definitely a problem with talent. And we are in the midst of the digital transition, aren't we? And McKinsey says that AI leaders outperform their industry peers by a factor of 3.4. And there's also another quote I want to give you from actually the VP of engineering at ExxonMobil, who says that AI is foundational to the technology suite that will enable the energy transition at scale and with speed. But what does it all mean? What does AI mean? It's a generic term, isn't it? So it's just mounting generic AI on top of existing solutions. The solution? Maybe not. And I'll give you a couple of minutes maybe to think about it on your own whilst we start with the first poll, which actually says, where are you in your AI journey? Are you one of the industry leaders McKinsey was saying, or do you want to reach them and reduce the gap? So let me open the poll for a second and I'll see if there are already some votes coming in. For now, I can't see any votes, but I'm not sure if this is because of my interface or the votes haven't come in yet. Give me a couple of seconds.
Dennis, we've got a fair number of responses now. It looks like about 75% of the respondents say, we know we need AI and we want to explore solutions. And then a couple in each category for at the very beginning and looking to learn more, as well as currently using AI and loving it.
Okay, so this is a fair share, and I hope I can, at the end, excite you all about this topic and see and give you a better impression where actually AI and especially our optimizing brain can help you. So I spoiled it a bit already. So I was leaving you with the questions: what do we actually need to actually become industry leaders and help with the power of AI to reach our sustainability goals and overcome challenges of, for example, talent degradation? And the solution is one holistic solution. We call it an optimizing brain for your plant. And throughout this presentation, I hope I can show you why we think this is needed and why it is so powerful. And speaking of powerful, let's think about our brains. Our brain is able to solve complex and previously unsolvable problems, like the energy transitions. Our brains are able to solve something they've never seen before, even though the solution path is not yet visible to them. Also, our brain is able to fuse many different information, many different types of data through our senses, like our eyes, our skin, to one perception of reality, one mental model. So think about your plant. Do you just have one version of reality or just one model to cover all processes and objectives? Also, our mind is guided by the fundamental first principles of nature. And what do I mean by this? Think about back in time when you were a child. You understood gravity, that you will fall on the ground before it was taught in school, wasn't it? So our mind is guided by these first principles, even though we might not be able to put it into an equation. And any model of a chemical process needs to adhere to certain first principles, like mass balance, doesn't it? Maybe the biggest fun part of this presentation, have a look here on the right-hand side. Can you read it? Give you a couple more seconds. And most of you, I guess, will totally be fine in reading it. But why? It's actually complete nonsense what's written down there. Only the first and the last letter of every word is at the right place. So what's our brain able to do? It's actually able to compensate for heavily impaired and unexpected data. It can contextualize and make meaning out of it. So is all the data at your side in a perfectly organized and in good state? Are there some things where actually we as engineers or operators contextualize? And also think a bit more about this if you see a process which might be completely different when you look at the differences, but we as humans can see the similarities and actually make conclusions and actions out on it. And finally, our brain, our nature as humans is able to learn complex control through experience, trial and error. And what do I mean with it? Think about how you learned, as in this picture, how to walk. No child was taught at a whiteboard session of very complex control laws how to walk. Actually, it stumbled, it fell on the ground several times, and then it gained experience and started walking and execute very complex control tasks. And learning through trial and error, there's actually a field in machine learning called reinforcement learning, which does exactly this and is then able to take action. And coming now back to the topic of this presentation, when we want to combat climate change and accelerate the energy transition, there's no time to wait and learn. Learning and gaining experiences is linked to times and years and decades in, for example, school or university. But we have no time. We need to go past monitoring and execute plant sustainability objectives today. So how are we going to do this? The new processes, for example, need still years and decades to be established. So thinking about this, what do you think? Where at your sustainability objectives can AI help today to achieve those? And let's start another poll, and I hope I can see it this time. Okay, I found the trick. I need to submit on my own. I won't tell you now what my answer was, but let's see. Okay, we have the majority, 75%, going for all of these objectives. And then we have maximize energy efficiency, 20%, low emissions, 10%. Maximize energy efficiency seems to be a hot topic, and I think it's pretty much associated generally with AI. Getting more efficient, getting more out of the existing, and I think this is quite valid. We have not yet minimized waste produced, which is interesting, and we'll discuss later, as well as enable renewable processing. But we have 7 all of the above, which I guess include those. So I guess you're pretty convinced, and it might make sense when you join such webinar that you think so. So I hope I can over the upcoming slides show you a bit more what AI might mean for those objectives. So starting now with a real life example where our optimizing brain is actually applied today. So this is a petroleum coke calciner, I guess a unit not in every refinery, but at least linked to the refining process, and very important for the production, for example, for aluminum in smelters. So what's our optimizing brain doing for this unit actually to achieve their sustainability objectives? It's actually improving the yield of this unit by about 2%, reducing the usage of natural gas 15 to 30%. And with this, the customer saw a reduction in 2,000 metric tons of CO2 per year. And how is the optimizing brain doing it? This is actually, even though it's just a simple standalone process, it's actually quite complex because you have very, very high temperatures in this burn zone And actually this to predict is extremely complex, as well as you have quality targets, like your real density for a coke. And this actually is also then determined by burning of two different materials, natural gas and the coke itself. So all these different parameters play together that it is very complex to model this, or even unsolvable to model this with first principles and standard assumption. So there our optimizing brain, with all the features I've explained to you earlier, comes in and takes control over this process and delivers these KPIs. But this is just one example. So let's talk about this a bit more holistically. So this is a relatively standard hydroprocessing plant. You might see similarities to existing gas oil hydrotreaters, co-processing plants, or even complete new bioprocessing plants. So you have different feed sources from these two reactors for hydrotreating, dewaxing, etc., etc. And then you split your products between the desired and undesired products, or depending on your relative product demand. So as you see on the top, why do we claim this is previously unsolvable and closed loop? Let's think how we actually solve and optimize such problems. So this process is not always in steady state. It gets disturbed 24/7 by certain things like the feed quality, especially if we think about biocomponents, well, bringing always a new qualities, feed composition. If we think about a refinery setup, we might have different upstream units like CDUs or cokers. Then we have catalyst activity, which will change over time. It's not maybe as quick as the other both I mentioned, but this will change the process over time, years and months. So if a process is disturbed, if it's not always on steady state, we need to take decisions, ongoing decisions, to reach our constraints, which we define. If we reach constraints, we are getting the most out of units. So what might these decisions be? Yeah, the bed temperature, for example, who counteracts degradation of catalysts, the hydrogen distribution between reactors to steer certain reactions, but also maybe on the back end if we need to do a hydrogen purge, as well as traditional decisions like a cut point. And then we need to reach our constraints, which can be catalyst life cycle, recycle gas purity, or very standard product specs like Cloud Point or cetane for diesel. So our industry, I think, is quite good in reaching constraints. We all have a mindset reaching constraints and getting the most out of our assets, don't we? But there's more to it, and I put it here at the corners of this slide. There are also very, very different objectives. And maybe every role and every contributor to a refinery optimization might have difference. So we start with decarbonization through yield improvement at the top left. So what do we mean by this? Actually, if you have a certain product demand, a certain product is needed, and I guess the best example might be on the long run diesel, which will still be needed for long haul trucks rather than naphtha, as we can electrify personal vehicles. So actually we can decarbonize with the same amount of oil in the ground if we steer our processes more and more to the desired process and decarbonize to improving the yields towards our liking. This can also have other implications like increasing the yield, the total yield of all the products by using the same amount of utilities, where I'm coming then to the second part, the maximization of energy efficiency. And I guess as the majority of you have clicked on this on the poll, I guess I don't need to explain that much, yeah? Maximizing energy efficiency in a 24/7 manner is an objective that is steered against by certain folks in the refinery. And if we think about the example we had earlier from the calciner, this very complex trade-off for the decarbonization through yield improvement, the burning of the own produced coke, the own feedstock, rather than the maximizing of energy efficiency, using external energy sources like fuel gas or natural gas in this regard actually is very complex to do in a 24/7 manner, especially if we have ongoing disturbances and maybe varying constraints. Maybe not that intuitive are the two at the bottom. And respect environmental limits, I'll want to give you an example out of my career in operations. When we were thinking about environmental limits, I'm thinking now about furnace emissions constraints. I was on my shift duty and I was going to the control room every day, and the environmental limits haven't changed. I was observing what the operators were doing, and everybody stood against the same environmental limit, and everybody reached it. But the how was entirely different. And how can we think about an optimization when the how is so different? And I think then this links then nicely back to the point we had before with the energy efficiency, meaning just reaching an environmental limit and keeping our plants within its regulatory constraints might not be enough to keep it optimized in a 24/7 manner. And the final point, optimizing of renewable processes, I will actually give you another real-life example here with this time series plot. So we have plotted certain variables here, which is an objective function, the margin of this unit, the feed rate to this unit, bio feed to the unit, which is which was in this case untreated vegetable oil, then makeup hydrogen, purge hydrogen, and diesel product qualities like sulfur and the flash point. So what did actually happen here? Yeah, the hydrotreater was running on a conventional mode, and at this point in time here, at number 1, they were increasing the feed to the unit by 20 tons an hour. The impact on the unit was relatively minor. Yeah, we see here a slight increase in hydrogen, which is needed. Purge remained closed, and the sulfur did rise a bit. Yeah, this customer was still not in violation, so all good. So maybe we could have optimized with the hydrogen here a bit more, maybe a bit less to just reach this constraint. But yeah, this was standard operation, and I would say almost well optimized. Not much to criticize here. But then we go to point 2, and as we all experience now with the transition to renewable fuels, I guess we have experienced this. So we are starting to run the bio feedstock here. We do a 10 ton per hour swap to the conventional hydrocarbons. And then let's see what happened here. The first thing to note here is that there was no reaction whatsoever of this hydrogen stream. This hydrogen stream was arbitrarily hired with this swap and feed because more hydrogen was needed for the treating. But as I said earlier, it was arbitrarily because the unit wanted to be on the safe side. So they were driving actually away from their constraints. And how can we see it? Once is they actually had excess hydrogen in their cycle. They needed to purge. Honestly, obviously, we all know we need to purge to keep our recycled gas purity. But as the recycled gas purity was not measured, this was actually an overly conservative assumption to just go for a lot of purge to keep this purity high. And actually, there was also too much hydrogen partial pressure in the system, as you can see here, as the sulfur in the unit without having the target and another unit to reduce this quality giveaway was further reduced, and the actual margin of the unit was significantly lower as before. But it doesn't stop there. So after a couple of days, they stopped their co-processing campaign and almost switched back to normal operations. But have a look here. So the hydrogen is still relatively high compared to what we've seen previously. Okay, we have a 5 ton per hour increase. But actually, it's that high because still purge is done. And as I said, with unmeasured qualities, we actually are still in an unmeasured and unknown environment, where then our diesel sulfur again is rising to a certain point, but to which certain point? Just until the next bioprocessing campaign is done, it goes down again. So a lot of talking and explaining at this scenario that you might be very familiar at your own side. So what's the point I actually want to make? With these processes and these many new things, we actually need to use digital tools and our digital capabilities to further enhance our understanding of these processes before we actually just do arbitrarily and with best engineering practice made decisions. So meaning we need to enable us engineers to be able to make informed decisions rather than decisions to just stay on the very safe side, far away from our constraints and far away from an optimization. So what's needed? Can just one person at the refinery make those decisions and to drive this unit again back to an optimized state? No, we need to have the entire refinery aligned on one model because we have one reality, one goal, sustainable optimization, the topic of this webinar. So I brought four groups here of a refinery team which is responsible for the optimization here. And the goal must be to get all of these together. And the position on this graph is actually not random, because I think the planning and economics team has an idea what the ideal yields are, what the product demand is. Process control engineers can tune their models in a way that we run the process on the highest efficiency. Operators have to stay within any given limit of the unit and need to steer the unit in the most efficient way toward this. And the process engineers are there to develop and get, for example, new biofeedstuff into the unit. So what does it all mean? The collaboration of all those can accelerate the energy transition as all bring their own objectives, their own little world together into one holistic model, one source of truth. We call this then evidence-based collaboration, where all can work together on the one goal, the sustainable optimization, rather than opinion-based collaboration, where everybody's just focused on their one objective and their one tool and might miss a perspective from someone else or the reality of someone else. So let's see, we have this. We have evidence-based collaboration. And everyone is aligned on one perception of reality. But as said earlier, just knowing this is not enough. We need to take action and we want to optimize this process. So we need to do a very complex, dynamic, and nonlinear optimization. But let's start by thinking how we optimize. Yeah, we have a model of the plant, a neural network, as we provided with Immubit, which might be very strong. Yeah, we believe so. But every model at the end, as I was taught in school, is an abbreviation of reality. So even though everyone is aligned, we also all need to be aware that there's model mismatch. Independently how good this model is, this is a regression-based model, first principle-based, or a neural net, as said. So how do we traditionally then optimize a process based on a model? We do it with a solver. The solver goes through a certain algorithm, tries to drive the model to a more ideal state, and tries to fit this state then back to the reality. But what does it actually mean? As a model has mismatches, there's also a mismatch and uncertainty. So not only the way toward the optimum, but also the optimum itself is not 100% clear, so there's uncertainty. And think about what we do as humans. How do we tackle uncertainty? We tackle it through experience. And this is actually what we do at Immubit to tackle a very complex optimization problem. We solve this through experience. Nonlinear controller solved through experience this very complex optimization problem. And I'll explain you a second how we actually do it. So we built a virtual simulation of the plant. The one model, everyone is aligned. It's a neural network. And then we apply reinforcement learning on top of it. And what does it mean? Actually, an algorithm does hundreds and millions of times trial and error on this virtual environment. And as it gets reward and punishment, it actually gains something like human-like intuition experience. And by the way, this is the way how self-driving cars learn how to drive. There's no one programming self-driving cars out there. Actually, they take the car on a test drive and the reinforcement learning algorithm does decisions, firstly based on trial and error, later on its own generated experience. And when a decision is wrong, a safety driver can correct and teach the algorithm what to do. But there's no way we can take a plant on a test drive, is there? So actually we need this virtual simulation of the plant, and this needs to be as best a reflection of reality and have all the perspectives in there to actually give the model, the reinforcement learning model, a good feedback structure. And then once it's finished learning and this is vetted and scrutinized by engineers, we can actually apply this at your plant to take action, going past monitoring and taking action minute by minute to solve very complex problems never solved before. But we need to understand this, don't we? As I said, vetting and scrutinizing of engineers before. So we understand this at Immubit, and we want to make it as straightforward and as simple for the engineers, for the domain experts as possible. And how do we do it? We try to visualize what's actually going on in the neural net and how the relationship between all potential variables are. For example, we have here these gain histograms. A gain is just a one-to-one relationship between certain variables. And plant experts know that these relationships might change over time. And this is actually reflected here in the gain distribution, which actually shows that, again, a one-to-one relationship between two variables can change, which actually fits to first principles and research as seen there on the left-hand side. And I want to read here this customer quote. After Immubit's evaluation, they presented our data in a way we had never looked at our data before. And what does it mean? Actually, with the explainability of this digital tool, actually the customer learns a bit more about their real life process. And isn't this amazing that actually, and this is where digital tools are for, aren't they? They're there to serve us humans. And actually our tool is able to give you more insights to the plant. But enough talking. I would very much like to show it to you now. So I'll go here on the Immubit platform, which has this landing page where you can always see the model builder, model evaluation, the performance step, and the DLPC Cloud app, which is just a mirror of the on-premise app. You can always go for a tour, or via help access our knowledge base or Immubit Academy, which is a learning management system for engineers to learn even more about our optimizing brain and how models are built and trained. So for now, as we want to explain it, let's go to the model evaluation. And in this case, go for an FCC and a vector regenerator model for this certain process. So here you can see then all potential models which were trained on this process, and we just go for evaluation here. And then you can see these gain histograms I talked about earlier. In this matrix, you can see all the CVs, which are the dependent variables. And further down, all the independent variables, so the variables we can manipulate, and the disturbance variables, the dBs. But you do not only get these histograms. So let's have a look here. We have the CVs, that are our emissions. And then on the left-hand side, we have then our dBs, our MVs. And we can, for example, look here at all the scenarios where this relationship between CO and the reactor outlet temperature is positive. And by selecting this, we can actually then track this back to other one-to-one relationships. As we know, our plants are more than one-to-one relationships, so we can actually analyze here, is this one-to-one relationships also impacted by other relationships or not? But not only this, let's take here another example where we actually can then look about the gain development over time. So we have here the CO versus the dense bed temperature. You can see here in every point in time where the gain was negative and now positive. So we might actually be able then to correlate certain real life events to these data points. And not only this, you can also check the arrow on the top, all the real life data over time at the bottom, zoom in and have in a very quick and agile way all the data of your process and also what the model got out of it. And for me, the most fun part, it becomes when we go to the episode evaluation, or you might call it what if scenarios. And you can actually then have a look how the response of my variables are to certain manual input changes. So we have here an episode, and then we can say, okay, this episode, nice and good. This was the past, but what if I would have changed something? For example, in this case, if I would have increased or kept my ROT steady rather than reducing it. We can clearly see here that the regen superficial velocity would have risen slightly, whereas in real life it went down. And this is not only just limited to one single what if. Actually, we can also do manipulation in our dBs, so something we can never do in reality. But as this is just a digital tool, yeah, we can actually assume, okay, what if this dB, the airflow, would have stayed constant? And with this, we might have seen this reaction on the CVs, but also done something differently, for example, on this coil outlet temperature here of the furnace. So, for example, just driving it down here for a bit on this ramp. So, yeah, I guess all this pulling together, and we can see again here the results where the O2 of the stack slightly went down, and the other was left almost untouched. So all this together, a very, very quick and nice tool to actually make it explainable and understandable, and making us engineers learn even more about our plants with this digital tool. But again, we want to optimize and we want to install this on premise. So we need to make sure that safety and cybersecurity is not an option. We need to adhere to safety and cybersecurity. So as said before, we extract this reinforcement algorithm from the cloud, install it fully isolated on premise, and only send data for monitoring back through your existing historian for evaluation. So there's actually the same interface like you would have with existing advanced process control systems. So coming back to the final point of collaboration, and this is something I won't show you in this webinar, and I hope we might discuss about this later. Actually, with the collaboration of all these people, we have built tools not only to analyze historic scenarios and do what if scenarios on a human basis, but also to challenge and work with an always optimized reinforcement learning solution. And it only takes 15 minutes for an engineer or an operator to learn this and then be part of the discussion, be part of the solution, not the problem, not blocking with their own perception of reality the progress fusing all together to one mental model of the refinery, of the process, of the optimization, and to deliver sustainable optimization. So I'm always almost done with this presentation. I want to give you a quick overview here about our recent successes. So we actually are able to improve the energy efficiency of to up to 30% of certain refiners with a margin uplift of 30 to 50 cents a barrel. You can see here the customer testimonials, where we're actually working with seven out of the top 10 largest US refiners. Some models are engaged for more than 5 years with 7 closed loop optimizations currently running. And with that being said, I hope you got excited about our solution, our optimizing brain. And I want to invite you to actually take on the challenge and challenge the optimizing brain and see if you're better in tackling climate change. And this optimizing brain, as you heard, is a completely new approach, leverages the full potential of AI, then brings all the groups together into one perception of reality, accelerates the process of cross-group collaboration, and then we sustain the values over multiple years and decades and deliver value to our customers financially and in their energy transition journey. And yeah, with that being said, I'm very happy to get your questions and excited to get into the discussion.
Awesome, Dennis. We've got a couple of questions from our audience. I'll start with an easy one for you. When we go back to thinking about the 3 pieces of the Immubit product and think about the simulation that we do of the whole plant, is that virtual simulation based on first principles models?
Yeah, so no, we actually believe that the full potential of AI we can only get when we take a data first approach. So this is based purely on your plant's data. However, we all know that data might be misleading. We had enough examples, for example, if you remember the text where actual data might be misleading. So we actually need to bring domain expertise, first human brains and then artificial brains, to guide these data, these real life process data by first principles to actually achieve the best way of the virtual simulation of the plant, and then leverage the reinforcement algorithm to optimize it. So quick answer, no, it's based purely on data and guided by the domain expertise with first principles.
And a follow-on question to that, when we're doing modeling data first, what are some of the advantages of this, or what are some of the downfalls of the first principles first based modeling approaches?
Yeah, if we think about first principles modeling, how do we get into a first principles model? With assumptions. For example, when we think about very rough models, we have certain examples like ideal gases, for example. So we need to make an assumption which might fit the reality and might not. And when we want to then apply this back to real life processes, we have actually destroyed a lot of the value, a lot of the potential, a lot of this information which actually exists in your real life data. So if you make an assumption, you actually exclude a lot of real and valid cases where actually your data embedded it all may be a bit hidden, and the AI is then very much capable of in unlocking these value potential for our customers by using their data to get a better understanding of their processes compared to limiting it by doing the first principles approach.
I have one more product related question. Is the optimizing brain equivalent to an LP solving with constraints and a maximum profit criteria? This question was asked specifically in the context of, is it done the same way as AspenTech DMC? Okay,
yeah, so no, the quick answer is no. And there are many aspects of that. So first is the optimizing brain is far more than just the optimizer on the controller who's applied on the plant. But let's focus for this on a second, as this is actually based on reinforcement learning. There's no solver. So as the solver for a linear program usually is the simplex algorithm, this actually, as it is based on reinforcement learning, has a pre-optimized solution, meaning there's no solution conversions or flipping problem, because if you have one unit state, it will give you out the optimized solution in a matter of seconds, rather than solving and searching for this solution. And the other very important part here is that a solver always needs to apply it on a model. And I a bit alluded to the downfalls on this earlier, whereas our optimizing brain, through its experience, is always applied to the real life process and does not need to have this modeling, this model step in between whilst it does its optimization.
Thanks, Dennis. Another question from the chat. So would it be possible to detect false data in terms of transmitter issues, other data quality issues that are so common in refining?
Yeah, very good question. So the first and most important part is that this is no magic. Shit in, shit out, in a very informal language here, meaning whilst we build and train our models, we have certain bad data rules and certain tools which our implementation engineers or your domain experts can use to actually detect those bad data. But there's a second point to it. So let's think about a slow, maybe months-long meter drift. Actually, we want to have this in our data, because you won't in real life correct a slowly drifting meter always all the time. So actually our model should know and understand that this meter might drift and not be pushed into a wrong direction with it, meaning if it might be a yield meter, suddenly if it would drift, it might violate mass balance. So actually our optimizing brain then can understand that this meter drifts and the actual value to close mass balance is a bit off. So yeah, fault meters and bad data periods get excluded. And if we have slower, more degrading processes, we actually want to include this in the training of our optimizing brain.
Dennis, I want to go back to your comment on the slide that showed the deep learning controller and all the different personas, and it made the claim that it only takes 15 minutes to train an engineer operator on the optimizing brain. Can you tell us a little bit more about how that works when it's dealing with especially previously unsolved problems?
Yeah, it's a fun question. It's a bold claim, isn't it? Such a powerful tool, only 15 minutes. And before I answer these questions, let's say more in detail and scientific, it's actually a scientific answer. The reason why we come to this 50 minutes is actually that we did an experiment. So we used these tools that we have built through engineers at, for example, conferences who have never seen this. And there were more than 200 engineers until now who have participated. So they have never seen our product before, and they were more or less thrown into the situation. They were then trying to optimize a plan first, and then after this, analyzing the optimized solution of the optimizing brain. And the 50-minute then is at the end just an average. But how come that such a powerful and complicated tool actually only takes 15 minutes to learn? The reason is that our entire product and our entire vision is based on that domain expertise. Domain experts should use it and utilize it. Meaning our tools are, for example, when we evaluate and look at the solution of the optimizing brain, are simple time series plots where everybody is used to. And I guess all of you engineers have many, many time series plots. So we just take the existing mindset of us engineers and try to use it as good as we can. And so we are actually then able to show the impact of such a complex optimization with very nice and intuitive tools. And it only, again, takes 15 minutes to train an operator or engineer to use those.
So you spoke a little bit to how long it takes a person to get up to speed on the technology. Let's talk a bit about the timeline of actually implementing the technology. So can you walk us through how long it takes to get the model up and running from idea to closed loop execution, and what are some of the key steps along the way?
Yeah, if you have an idea, you can reach out, and usually we then do an 8-beat process. We call it economic validation, where we preliminary scope the project and give you, let's say, a business case where you can then present this to management to actually justify this project. Then, if you get a go, we actually have a 4 to 6 months process to actually get the optimizing brain running in closed loop. This usually starts with a kickoff and detailed design meeting, where we really, with our domain expertise and your domain expertise, define the scope. And then, at least the first project, our domain expertise start building the model. First by data exploration, so cleaning the model for bad data, for example. And then we go in multiple iterations of training. So first to build the simulation, virtual simulation of the plant, which can be creating of inferentials and the dynamic process model, and then train the reinforcement learning algorithm finally on top of this. This usually takes 4 to 6 months, not because the training takes that long. This is just usually a couple of minutes, hours on the cloud. The alignment and the human part of this takes usually the largest time, so that we at the end are, after this 4 to 6 months, are really sure that this is good and vetted. And then our very rigorous change management process starts, where our implementation team and customer success team works directly on the board with you to get acceptance and familiarity. And this takes another maybe two weeks then to get the operators at the board comfortable to keep our models and our solution engaged 24/7, always, all the time.
Awesome. So if we put a total timeline on that, what are we looking at? Like 6 to 9 months for total implementation?
Yeah, but this is the idea. If we think about the project, it's 4 to 6 months. But yeah, you need to scope and get the idea into a business case first.
And if you think about that in the context of the traditional APC or RTO projects that are implemented, still a pretty big improvement.
It sure is, and I guess this is something we are very proud of, as we have this data first approach, as we have these very strong SaaS platform tools. I think our customers at the end benefit a lot with this pretty much shortened timeline.
So I've got a kind of technical question about that data exploration phase of the project. So how do you make the data that the model needs to use during the reinforcement learning available to the Inuit platform?
So this is usually shared. So what our platform needs to train these models is minute by minute data. And usually we take, depending on the process, maybe 2 years, maybe an entire turnaround life cycle. So this amount of data, if you maybe think about, let's say, 4 MVs, 10 CVs, 5 DVs, which are about 20, 30, maybe variables, minute by minute data for 2 years. The amount of data is not that huge that you just can't just transfer it by traditional data sharing and data transfer methodologies. And then we just extract this to our data and train on the cloud on GPUs the model. So the data transfer at the end is not that much of an issue. And again, slicing and finding the right spot of the data is a almost hybrid process of domain expertise of the engineers plus certain digital tools which help to define, let's say, from a data science point of view, bad data.
Awesome. And I think one of the key points there is that our reinforcement learning is offline. And so that data is transferred once, used to teach the model, and then the model's running on live data after the reinforcement learning. And then I have one final question for you, Dennis. We'll close out with a good sustainability related question. So where in your eyes do you see a refinery and the biggest impact areas for reducing specifically scope 1 and scope 2 emissions?
Yeah, so important to see here is that there's no way that we see traditional technologies are bad. Still use the traditional technologies to make your move there. But where do you need an optimizing brain? You need an optimizing brain when the problem is complex and you cannot ensure an always right answer. And which areas are these? These are very complex and multiple reactions go on at a time. Or we are at regions like very high temperatures where we struggle to measure all needed variables. So coming back then to where do we think we can work best to reduce scope 1 and 2 emissions? So the first one, as you've seen as the example here, very energy intensive processes like the petroleum calcining. I'm also thinking about olefin plants, the steam crackers with very strong or very high carbon footprint nowadays. So all these where we have very high temperatures. But also, if we think about processes like conversion, so for the FCC, we all know with this reaction, we have an internal burn there as well. Or for a hydrocracker, we use hydrogen, which also has a very high carbon intensity. So summing it all up, either very energy intensive, high temperature processes, or where multiple reactions are ongoing, which also associate to a high carbon intensity.
Awesome. Thank you so much for your time answering the questions, Dennis, and for that great presentation. And for the folks who joined us today, we really appreciate you spending the hour with us. We'll follow up with you with the event recording via email, and hope to see you at an event or another webinar soon.
Thank you very much.